Merry Christmas, everyone, if you're watching this on the day this video comes out, or every year the anniversary of it. If you're not watching it on this day, welcome back, everyone. Today we're going to be going over maze generation with specifically using Prim's algorithm. Now, I have a video on my channel from a while back kind of going over this, but that was using maze generation and setting all of the tiles in the maze to either be a wall or a path. This time it's going to be still using prims, however, instead of a wall or a path, all the tiles in the maze will be paths, and instead we'll be putting walls as a thin line between them. So previously the maze looked like this, however this time we're going to make the maze come out like this. And at the very end I'll also throw in a little fun extra surprise into the maze generation to kind of spice it up and change it to be different than last time. So to start out, for the code I just have some very base code. In the main method here, I have a J-frame being created, and then in the J-frame, I'm adding this class, which is extending a canvas. We'll be using a canvas to draw the maze on the screen. And then I also have a few constants up here of the width of the screen, or the width of the maze, height of the maze, and then the tile width and height. And then in our paint method currently, we just draw 4 lines representing the box of the maze. So if we go ahead and run it, you'll see we have a box here. This will be what the maze is drawn inside of. These are just the 4 outside walls. So not starting with much. And then I also have real quickly a vector 2i here. This will help me with saving coordinates. Java doesn't really have a good way to hold just 2 integers in a coordinate style like this. So I went ahead and made my own small little class here. So all this will be on GitHub for you guys to see, so don't worry if you don't have this right now, you'll be able to see it later. So real quick, so right before coding, or while I start coding here, the way that Prim's algorithm works is essentially it does a spanning tree of ascents to where it'll pick a random point that has been saved to a cache array list, and from that point it'll see all the points around it, select the points around it, and if they have not already been visited, add them back to that cache and kind of keep doing that in a repetitive process until all the points have been visited or there's no points left in our cache. So to start out programming, our algorithm here, we're going to need to have 2 lists in our journey method. So we'll make a method here called generate. This is visited, if I can spell correctly. So the first list we will have here is called visited. This will store all of the coordinates that we have visited. It is an integer list though, because it is going to store the indexes that we have visited if the maze were a singular one-dimensional array. The reason we're doing this is because the vector 2i here is actually going to be representing a path instead of a location or position in the map. So more on that in a second, but the second one we will store is a vector 2i, and this is going to be called toVisit. So this is our cache here of points. So this list here is going to store our paths in the maze that we have currently are building up. So with each of these arrays here, we're going to first start by just adding 0 to visited. This will represent us starting in the upper left hand corner of our maze. And then what we're going to go ahead and do is manually add in toVisit. We're going to add a new 2 vector 2i's representing the path from 0 to 1, which will be representing this cell here and the path from here to this cell. And then we will also go ahead and add in this cell of 0 into the one below it, which will be the width of the maze, which is representing the path from here to here. So if you don't know how to convert from 2-dimensional to 1-dimensional arrays, essentially you think of this as 2-dimensional, and to get it to a 1-dimensional array, you take the y coordinate of the cell it's in, multiply it by the width of the maze, and then add in the x coordinate of here. So of course Java or arrays start at 0, so this is the 0th row, the first row, second row, third row. So we're on the 3rd row here. So we take 3 times our width of say 10. This will give us 30. add on 0 because this is the 0th index, and we would get, it says index 30 in a one-dimensional array. So we have added our 2 locations to our cache. This doesn't necessarily mean that these locations will be a valid path in their ending maze. As you can see here, this is not a valid path. These are only possible paths that we could choose from. So now we set up our main loop that drives the whole generation, which is going to go on for as long as this 2-visit cache, the size of it is greater than 0. So as long as we have possible paths we can create, let's keep iterating over this list. And in order to generate a new maze each time, we need to grab a random index from this cache here. So we use our rand that we created up here. So part of what I also pre-made is I made a random variable. So we'll go ahead and use our random variable to get a new integer from 0 to our visited size. So this will give us a random index here. And what we will do is also go ahead and just grab the vector2i associated with that index. So this is going to be the next position, or the next path, I should say, the next path. Go ahead and grab it. And before we do anything with this position, we need to first verify it hasn't already been visited. So in the case of here, this specific maze generation chose to build out this way and eventually came back to this position. So what happened was that the path from this tile here to this tile was already established. And that happened before it came back and chose the path from here to here. Now, if we chose the path from here to here and actually made that a valid path, we would create a loop, which is what we don't want. We want just one single solution for this maze. You can add in and out. You can also add in the choice and availability to create loops, which is a whole nother part of this, but I'm not going to dive into that right now. So we're just going to deal with one path through this whole maze. So what we have to do is we have to verify that the path from here to here isn't going to cross into a tile that has already been visited. So in this case, that is true. So we want to throw out this path from our cache and just skip it. So we're going to do that by simply checking our visited list here. And we're going to check if it contains the tile we are trying to go to, which is the next path, and I called it end. The end is essentially where we're going to. Start is where it's coming from in the path. So we're going to check that visited contains it. If it does contain it, we want to throw this path out. We want to remove. Well, we want to remove it either way. So what we can do is we can just go ahead and just kind of shortcut this and to remove it there. And if the visited path contains this, then we just want to simply continue this while loop. Don't do any of the following logic. So what is that following logic? Well, the following logic is to actually then add the ending position to visited. That way it can't be revisited in the future. So next position or next path dot end. And now we get into the next part, which is to actually break out and find the adjacent tiles. So if we're starting here, or if we're here, we need to find the adjacent tiles here and here that we can actually move to and add them to the cache. So the first bit is we want to check the above index, which is going to be next path dot end minus the width. So of course end is where we are going to. So that is the index in the visited array here of where we're going to, and we're subtracting width because remember this is a one-dimensional array, and in order to get the above position you want to subtract the width off, because if the width is 10 you would go 10 over and that would place you right one above. So now that we have the above index, we first need to check that 1, it is a valid place to go to, so that is above 0 because this is our 0 up here. So we have to make sure that it is greater than 0. And then we also have to check to make sure that it is not in visited. So So you might also be asking then, why do we need to do it twice? Why do we need to check if it's not visited here and also here? Why can't we just get away with here? We have to do it both places, because what happens if we say are here, we add both of these, and then later on, these were valid at the time. Later on, the maze goes around, comes back, and it knocks out that, or visits that tile. Well, now it's already in the cache, because it was valid at the time we did this logic, but now it is no longer valid. That's why we need 2 checks, because the maze will change over time, and what was valid isn't always valid at the time, or isn't always valid when we get there. So now that we have verified that the position can be visited, let's go ahead and add it to our cache. So go ahead and add a new vector 2i, so a new path, and the path will extend from our next path.end to above where we want to go. Nope, new. So that will go ahead and add the one above. Let's also go ahead and copy this 3 more times. So we have above, left, right, and below. So above's done. So now for left. So the left is going to be the index to the left of our current end index. And the left is simply just one less. It's going to be one index to the left. Pretty easy. And that will handle this. Now, instead of checking above, we need to check that it's not going off the screen left. However, we are in a one-dimensional array, so there really isn't a left wall. The left wall is actually going to be the width of the maze. So we have to check that we're not wrapping around from here to here in our index. Because remember, this position here and this position here are technically next to each other in our one-dimensional array. So we have to check that we're not wrapping around in that sense. And to do that, we are simply going to do a modulus of the width and check that it is not equal to the width. So width minus 1, sorry. If it was equal to width minus 1, that means we have gone from 0 on the column here, and we have looped around to the ending of the width. So that just does a quick check there. And we also have to make sure that it's not invisited, and then go ahead and add it in like so, just like above. Now right's going to follow a similar pattern. However, instead of checking if it's not equal to the width minus 1, we just got to check it's not equal to 0, because we're doing the reverse. We're going from width minus 1 to 0. So just check the reverse, go ahead and add it, and go ahead there. Below will follow, again, the same pattern, and that we want to, instead of subtracting the width, adding the width, and now we need to check that we're not going beyond the map. So the last valid index will be the width times the height. Well, actually, that's 1 above the max index, but that's why we're checking that it's less than this. And again, make sure they're not visited, and go ahead and add it in. So there you go. That is actually the full-on logic for this maze generator. So let me go ahead and clean this code up real quick, and then I'll show you what it's all doing. Okay, so I've cleaned up the code, but before I can actually show you what it's doing, we need to quickly do our render method. So if we scroll up here to our paint, so we need to edit this paint method to be able to show us the maze, because if we still run it right now, well, actually we can do this. If we go down here, if we call our generate method here, so we are calling it, we are generating the maze, but if we were to run it right now, we would still only see our 4 boxes. Okay, I was trying to determine why this actually wasn't running and working. It's because I forgot to change the right here to be +1 on the index. The opposite of why left is -1. So now let's go ahead and try to run this. And we should see our maze pump up here with just the border, just like it was before. That's because, again, we haven't told it to actually render the maze. We are generating it, but we're not actually rendering it. So to render it, we are going to first do 2 for loops. The first one will be for our y's. Oops. And the second one here will be for the x. So we're going to go through basically every one of the coordinates in our maze, so up here. So we're basically going to go through every one of the coordinates, going down in a line just like this, and we're going to check if the path going from the tower at, we're going to see what paths it has that are actually paths. And then we're going to draw walls on the one where there is not a path. So now that we got our for loops here, we're actually going to simplify the logic we do a little bit, in that we're not going to check all 4 directions, because then we would be drawing double the lines. Because if I grab the original maze back here, if we were to calculate the walls for this one, we would see that we would have a wall here and no walls in the other 3, which is fine. So we would not draw a wall in the 3 and only a wall here. However, if we were to then now get to this tile here, we would see we have a wall above it and a wall below it and none of the sides, but we would be double drawing this wall. So we would be doing double the work. So in order to not do double the work, we're going to only worry about the wall to the right and the wall below the tile we're at. That way we're only drawing one wall for each tile while still checking all of the walls. And so to do that, we need the index of the upper, I'm going to call it upper because it's going to be the tile above. So we're going to do a tile above and below. So the upper is actually where we are currently at. So it's just going to be y times width plus x, the equation I told you about before, for getting the index of a one-dimensional array from two-dimensional coordinates. And then the one below this is going to be the exact same thing. However, we're going to increment the y by 1 in order to get, the index of the position at the y that's 1 above it. Because remember, we're counting, our 0, 0 is the upper left-hand corner, so 1 below is actually increasing the y by 1. So now that we have this, we need to now know what our maze is. So the issue is we don't actually have a saved maze. So we're doing this whole generation, but we're not actually saving it anywhere. So the next step is to, in here, right when we add it to visited, we also need to add it to a global map up here. So let's go ahead and create a map. Let's call it private map vector2i. So this is our path. Actually, it's not a map, it's a list. We're just saving it as a list of all the paths of our maze. We'll just call it maze. Oops, so new hash, or no, sorry, list, not a map. So now that we have our map here, let's go ahead and add it here. So maze add, and we'll add in next path. So that will correctly add the next position to the map. However, we're going to run into one problem though. The one problem is that we are not guaranteed that these paths that we're putting in are always going to be in the format of above to below or left to right. It could go right to left or below to up because we're picking random coordinates and we're checking all 4 around it. So because of that, we need to properly align the path to go from top to bottom or left to right. So what we need to do is we need to throw in an if statement here. We need to check our next path, the start, and if the start is greater than the next position, our next path end, if the start is to the right of the end, so we're going right to left, or it is below the end, going bottom to top, we need to simply flip the vector coordinates. So we're calling new vector2i, and we're going to call next path end, whoa, next path dot end, and then after that we're going to do next path dot start. So this will flip the path. Instead of going, right to left, it would go left to right. It doesn't matter what the order of these two are. It's just what matters is that they go left to right or top to bottom. And then otherwise, if it's not true, we will simply add it like normal. And now we have all of our paths correctly aligned in this maze variable, we can go ahead and check in our draw method here. So we can go check if maze contains the new vector 2i of upper and lower. And I've already gone ahead and done equals method in the vector 2i's here to check properly. So it is checking for ones that exist. So if it contains it, we actually don't want to draw a wall. So we want the opposite of this, to where if it doesn't contain this, that means this path is not a valid path, or isn't a path to be able to go through. So we do want to draw a wall. So we'll go do G, draw a line. This is just how the canvas draws. We'll draw it from the X coordinate times the tile width, and then we'll draw it. So it's drawing it from x1, y1, x2, y2. So this takes a second to fully understand what the coordinates and stuff are, but once you kind of figure out, it's not a huge deal. So I'm gonna go ahead and do this, and we're gonna draw it. First, we're gonna go, this one is across. So it's because it's below this, we gotta draw it across. So the X is what's increasing, the Y is not what's increasing. And make sure I don't need this. And so what we should see is a bunch of horizontal lines like this showing where the bottom borders are. Oh, it's not going all the way because I did width instead of height there instead of width. Okay, so that should actually fix it to make it go all the way across now. There we go. So now it's drawing all the way across. So now we have done the top to bottom check. We need to do the left to right check. So we're only going to need to store one variable here, which is left. Right is very simple because right is actually just one index over. So left is y times width plus x, which we actually could have just used upper again, but so that way it makes sense. We'll call it left. Actually, we can just call this current. Let's make this a little bit simpler. Let's call this current. So our current position. And then we're going to snag this again here because we're going to check the current, and then we're going to check current plus 1 because plus 1 is going to go to the right because that's a 1 index over. And then we are going to draw it, and this time it is the y that increases by 1. And now if we go ahead and run this, we'll get a maze. There we go. Look how simple that was. Nice little maze all generated. So I'm gonna add some little code here, and that way I'm able to show you how the maze is actually generating and have a visual of it. So 1 second. Okay, so I've added some code here. Basically, I just added a timer. That way it'll progressively generate the maze. So it still generates it all in one go, but it'll progressively show the maze as if it's generating like that. So I go ahead and run it. You'll notice that it starts off as just a grid of all of the walls, and you'll see up here it's slowly actually building out the maze. You'll notice that it is seemingly choosing a random ending point that it's been. So it's breaking through walls and slowly building up the maze, and it's choosing a random point almost to like add a new path. And again, that's why Prim's algorithm works, is it just simply picks a point, adds all of the adjacent tiles it can go to that are valid to a cache, picks a random from that cache, and continues that whole cycle. So this gives you a real visual on how it kind of generates and how it builds. Obviously, this will take a while, so I won't let the whole thing run. But it's a cool visualization of seeing it generate the maze and seeing it knocking down walls, and how it actually picks the positions to go to kind of do a spanning tree or a breadth first search almost kind of looks for the generation there. So either way, that is that. So that is the maze generating. I will actually remove the code. I'll leave some of it there. So if you look in the GitHub, the code to make this visualization will be there. Obviously, it's not perfect because this is a JFrame. The rendering, it doesn't like a lot of rendering like that. It gets like that screen glitch for a second sometimes, but the code will still be there, so you can still visualize it. So what I'm gonna go ahead and do now is remove that code so that it just, or I'll comment it out so that way it's still there, but it'll fully generate the maze again. And I'm going to give you guys a little surprise here for the end to kind of show you how cool this algorithm is and some cool things you can do with it. Okay, so I've commented out the generation code, so now the maze generates just like normal once again, as you can see here. And what I went ahead and did do is I added a method here to load an image in from a file. So in this file here, I have two images. The first one's Merry Christmas. It just has a text Merry Christmas. The other one has a tree image there. And so what this method does is it'll read the image into a buffered image. It'll then go through all the pixels and it'll check the color of the pixel. If it's -1, which is white, it'll add the pixel to the visited list, which will pass in through here. And it'll also add the actual color there to a colors hash map at the very top. So what we're going to do with this is we're actually going to call this method from our generate, or actually right before we generate. Sorry, yeah, right before we generate, in our generate method, right before we generate, we're going to call this, we're going to call load images in, and we're going to give it visited, and let's do the tree first, so tree.png. So we'll go ahead and call it there, and then you'll notice that it won't actually do anything. It'll look weird. So it'll correctly generate the maze, and it'll correctly not visit any of these tiles in here because we told it not to. That's the whole point of adding the position that is not white to this visited array. So basically, we use the tree, we check all of the pixels, whichever pixel is not white, we say, don't visit this, leave it as is. That's the whole point of adding to visited. This says, do not put a path to here. We're going to essentially mark it as unpathed. And we're going to create a Christmas tree. So basically the maze is going to generate around our image. And by not having color yet, you can see that it is correctly not actually generating inside this tree. So we've correctly made the maze generate around it. So it's found a path around an object there. And if we go to our render method here, so now we can go ahead and just quickly check if our colors map contains the key of a new vector2i. We can just use x and y this time because we're actually treating this as a location or a vector coordinate instead of a path. And if it does, we will simply set the color of the graphics here to the colors get our vector. Actually, we can, yeah, that's fine. We'll set the color there. We will then do a fill rectangle at x times tile width, y times tile height, and the size of tile width, tile height. This will create a, this will draw a square, essentially, or if your maze was a rectangular tiles, it would draw a rectangle at that location, say offset for the width and height of the tiles. And then we'll go ahead and set the color back to black. That way the lines still stay black. So color.black. And now if we go ahead and run it one more time, we should see our colored Christmas tree all in our map right here. Nice and fancy and snazzy like that. So again, the maze correctly goes around these tiles here. It goes around them. It does not generate the map inside here, as you could see from before. It leaves those untouched. And now if I go up here and change this to Merry Christmas, you'll see that it even works for finding paths through these letters here. Obviously, it can't find a path in these R's inside here, so it can't actually generate the maze in there. But anywhere it can reach, it will generate the maze too. So that is a cool aspect of Prim's algorithm. And that is Prim's algorithm for you. Hopefully you guys enjoyed. Have a happy holidays, and I will see you guys all next time. Peace out.